For this second question, before I solve, I need to clarify this notation here. Well, you see, whatever that is, if you're integrating over a path, always the idea is divide by dt and multiply by dt. Okay? That's always the idea. And then if you look at this one, this is really like a dot product where you have x plus y comma 3x minus y dotted with dx dt comma dy dt, right? Now what does that mean? That means that this right here is the vector field f, fxy, and this one here is dr dt. Okay, so this is just another way of writing down f dot dr. It's just a little harder to understand what's going on because it means this. Okay, so when you think about dx comma dy, you should really think of this as dr. Okay, so what is r? R is this position function where it gives you the location x and y at each time t. That's what r is, right? So when you have dr, you should really think of this as dx dy, so that what you're seeing here, that one's really like integral over c of f dot dr, where f is this comma that, and this comma this is dr. That's the way you should think. So this is just part of a note, not really a part of the solution. In every line integral, oh, by the way, I forgot to say something interesting about this, the word line integral. So you may notice that I keep saying C is a path, right? So when you do this f dot dr, you're always integrating over some path. So why aren't people calling that a path integral? And the answer is some books indeed do. So some books would call this path integral, but path integral is usually reserved for this very complicated thing called Feynman path integral for quantum mechanics, quantum field theory. So because of that, that's a reserved word, so people just use this as a line integral, even though C is like, it's not always a line, it can be curved, it can be any kind of curved path from 2 points, that's what C is. But inconveniently, people call that line integral, and that gives you an impression that you're integrating over a straight line, but that's not true. So here, the line should really contain things that are curved as well. Okay. All right, so how do we solve this? Again, the idea is divide by dt and multiply by dt. This is true for all line integrals. But again, the challenge is how do you parametrize a straight line from here to there? Well, actually, for straight lines, there's one particular way to do it that's easier than the others. That's what I find, and what I mean by that is like always do terminal minus initial to get the direction vector. So the direction vector. Remember that line equations in 3D requires a point and a direction vector, right? And if you're given 2 points, just subtract the 2, that gives you the direction vector. So terminal is 3, 4 minus initial, which is 1, -1. That's the terminal point of the path. This is the initial point of the path. So you do terminal minus the initial, which gives you 3 minus 1 is 2, 4 minus negative 1 is 5. So that's going to be your direction vector. And what you want to do is you want to choose the initial point as your point. So see, in the line equations that we learned for 3D, I said it doesn't matter which point you pick, but since path requires a direction, you should always be aware of the terminal point and the initial point. This is beginning and that's the end, right? So you should always do terminal minus initial, and then x1, y1 should always be picked as the initial point, okay? Then you use the formula for the line equation, which was like, it's x1 plus at and y1 plus bt, right? Well, in 3D, we learned it as z equals to z1 plus ct, but this is 2D, so we don't use that. So this is not relevant here, because it's 2D. So we just have this, and because the direction vector is a comma b, a is 2 and b is 5, here's what we get. We get 1 for x1 plus 2t, because a is 2, and y1 is negative 1, plus bt, b is 5, so that's what we get. And indeed, when t is 0, what do we get? If we plug in 0, what do we get? 1 comma negative 1, right? This place, right? And then if, for what value of t would you arrive at 3 comma 4?
1.
1, right? If t is 1, when t is 1, 1 plus 2 gives you 3, negative 1 plus 5 gives you 4. So you indeed arrive at 3 comma 4. So if t moves between 0 to 1, we get a straight path from these 2 points. Okay? And this is a nice way to get a parametrization for any given straight path between 2 points. If you're given 2 points, always do it by steps. You just do terminal minus initial. That's going to give you the direction vector. And then use the initial point as x1, y1, and just write down the equation for the line. Well, equation for the line for 3D, the parametrized version. And then if you look at it, what happens is that when t is 0, you're going to be at the initial point. When t is 1, you'll always be at the terminal point because of the way we made it. Okay. All right. So that's what we have. And therefore, now we can calculate integral c x plus y dx plus 3x minus y dy. Remember, these are the components of the vector field, but we are evaluating those at these locations, right? So your x will be replaced by 1 plus 2t, y will need to be replaced by negative 1 plus 5t, and dx should be written as dx over dt times dt, right? So what is dx over dt? Dx over dt is?
2.
2, right? So we just rewrite this as, well, let me just write it as this one first. X plus y dx over dt plus 3x minus y dy over dt times dt, divide by dt, multiply by dt, and t goes from 0 to 1. And then x plus y is this plus that, right? 1 plus 2t plus negative 1 plus 5t times dx dt means you're differentiating this by t. That's what this means, dx dt. So you differentiate that by t, you get 2. Plus 3x minus y, so 3 times 1 plus 2t minus negative 1 plus 5t times dy dt. What's that? dy dt is 5. And then dt. And then That's going to give you, let's see, 1 and negative 1 cancel, so 7t times, that's 14t. 3 minus negative 1, so that's 4. And then 6 minus 5 is 1t times 5. 8t. So that this is going to be from 0 to 1 of 20. 4 times 5 is 20. And then 14 plus 5 is 19. So that the interval is 20t, 19 over 2t squared. Then you're plugging in 1 and 0. So you get 20 plus 19 over 2. And we like improper fractions, so turn this into 40 over 2. So the answer is 59 over 2. Or in decimals, this is going to be 24.5.